Okay, in this video we are going to discuss transformer polarity and multiple winding transformers. One of the things when we are looking at a transformer for terminal labeling, we are going to use what's known as the ANSI standards, which stands for the American National Standards Institute. So that'd be ANSI. And so what ANSI says is that when we are facing a transformer, we basically face the transformer with the low voltage side nearest to us and the high voltage side away from us. And when we do that, we must always label H1 on the upper left hand corner, and the other end of the H1 winding, of course, is, or of this primary winding or H winding, is H2. Now, how we label the secondary when we have it face this way is really what it's talking about when we're talking about the polarity of a transformer. So in this case, if we were to have an additive transformer, the X1 should be exactly the opposite corner as the H1. And the other side of the X1 winding will be labeled as X2. So that indicates the polarity of the transformer. So let's just go ahead. I'm going to erase this, and when we start getting into a little bit of the understanding. So a transformer with additive polarity is what's indicated here. And you'll see that the terminal markings are not adjacent, but across from each other. So kitty corner to each other here. And that's how we know that we have an additive transformer. So whether we have an additive or what we'll look at next is a subtractive transformer. When we're just using a transformer by itself, it really doesn't matter too much. But when we start paralleling transformers and they have different instantaneous polarities, or we start connecting up single phase transformers in groups of 3 to make a 3-phase transformer, it becomes very important because we could cause a short circuit. So that's why this polarity is so important. So let's look at what is happening with an additive transformer. So if I apply 240 volts across the primary here, it's going to have a 240 volt drop across this winding, and it's going to induce 120 volts across the secondary, whether it's additive or subtractive. But what it comes down to is that when this point is, let's say, negative here, which point is negative on the secondary at that same moment in time? Well, it turns out that when we have an additive transformer, the way it's wound, the direction it's wound in relationship to each other, that when it's additive, the X1 will be negative at the same time. So both sine waves are in the same direction. And we do a little test on transformers. When you get here to do the lab, we are going to be doing transformer polarity testing. And what does that look like? Well, we take supply voltage and we put it across the H1 and H2 winding. And then we put a jumper from H1 to its adjacent terminal. So we don't really know what's happening here yet, which lead is labeled as what. So we jumper it when it's live. And then we put a voltmeter across from H2 to its adjacent X terminal. And then we'll energize it. Now, if this transformer is additive, the two voltages, the applied voltage and the induced voltage, will add. So we'll get 360 volts. If I see that the two voltages add, that means that I have an additive transformer. And if I have an additive transformer, I have to mark the terminal kitty corner to H1 as X1, and then the other end of the X1 obviously is X2. So that's what an additive transformer is. So it all just depends on the way that this thing is wound. So we're looking at a 2-to-1 transformer here. 240 volt applied to the primary, induces 120 on the secondary. We jumper H1 to its adjacent terminal, put a voltmeter from H2 to its adjacent terminal. If the voltages add together to get 360, I've got an additive transformer, so I must label them this way. Let's now look at a subtractive transformer. Okay, so a subtractive transformer, same start. We face the X's closest near to us, and the other side, the furthest points, will be the H. So we always put H1, or we start with H1 on the top left, and then the other end of H1 is H2. And once again, this is a 2-to-1 transformer. And we apply our rated voltage to the primary. It induces 120 volts on the secondary. And if the transformer we purchase has X1 adjacent to H1, we know we've got a subtractive transformer. And then the other end is X2. X2 and H2 are on the same adjacent side of that transformer. Now, if we don't know what the polarity is of this transformer, we do the test. Same test that we just did. So we apply rated voltage, or a voltage, to the primary. So in this case, we're going to apply 240 volt, and it's going to induce 120 volt on the secondary. We jumper at H1 to its adjacent side, and then we connect up a voltmeter from H2 to its adjacent side. Now what does this look like? Well, due to the fact how this is wound, we still have the same applied voltage, just like we did in the other test. It's the same test, 240 volts. But now the induced voltage is still 120, but it's exactly 180 degrees out of phase with the primary voltage. So it's opposite. So these effects, the 120 and the 240, cancel each other out. So they subtract. So 240 take away 120. If our voltmeter reads 120 volts, right here, we know that we've got a subtractive transformer. And if we have a subtractive transformer, we have to label it with X1 adjacent to the H1 and H2 adjacent to the X2 transformer. So that's what a subtractive transformer, how it would be labeled. And our polarity test is to determine how to label the X windings, essentially, following these ANSI standards. All right. So we'd get 120 volts when doing this test. Subtractive polarity is typically used for transformers over 200 kVA. And where else you're going to see this is you will see it on a CT as well. It's also subtractive polarity, so instrument transformers. All right, the next one is multi-winding transformers. So you can get what a multi-winding transformer is something like this. So on our H side here, we've got, this is an example. It's not the only type of multi-winding transformer you can get. You can get them with one winding on the primary, two on the, or one winding on the H side and two on the X side. But what it really is that we have two windings, two H windings, and we have two X windings, and they are wrapped around the same core. So in this case, we're showing you an additive polarity multi-winding transformer. And so same concept happens, is that H1 is on the top left, and then the other end of the H winding, first H winding, is H2. Notice how they cross there. Okay, so that's important because we're going to be putting these windings in series or in parallel with each other, depending on our voltage. Then we have H3, so that's the start of the second winding, and the other end of it is H4. Because this is additive, the X1 winding is across, or diagonally across from the H1. So X1 is here. The other end of the X winding is X2. Notice how they cross. And then X3, this is how we draw it. So when you get used to drawing transformers, you got to be able to draw it the same way. X3 is the start of the second winding, and X4 is the end of the second winding. Okay, so let's get into talking about these multi-winding transformers. Let's look at a subtractive. Subtractive multi-winding transformer. Notice this same deal, H1 top left, but now X1 is adjacent. And of course would label accordingly The other end of X1 is X2. And this is a subtractive transformer. The X3 is the start of the second winding, and the end is X4. All right, so moving on. What is a multi-winding transformer? Well, multi-winding transformer basically has two ratings. So on the H winding, or the high voltage side, it's rated at either 240 volts. So if we were using this as a step-down transformer, our primary is the H's, and it could be connected up for a 240 volt supply or 480. And on the secondary, or the X side, I could connect up the secondary so that it could put out 120 volts or 240, depending how we connected it. So if I had a 480 volt supply, so when we're thinking about this is a 2-to-1 transformer still. So the way to think of this is that if we had resistors, equal resistors, okay, and I put a voltage across this, and let's say that they're both whatever, 50 ohms or something like that. If I put 480 volts across these two resistors, each one would have a 240 volt drop. Okay, so I'd have to put those two resistors in series. So same thing, if I put 480 here, I'd have to connect them in series. So there's only one path for the current to flow through both windings. Now each individual winding is only rated at 240, but because we connected them in series, they will only see 240 volts each. Now what if I had a 240 volt supply? Well, I could connect these, oops, back. Where are we at? There we go. I could connect these up in parallel, these resistors, same two resistors, if I had a 240 volt supply. Because they're in parallel, each resistor is only going to get a 240 volt drop. Well, this same concept applies to the primary of our transformer. If I have a 240 volt supply, now across the top, I would connect these up in parallel. So now, if we look, here's line 1, it's attached to H1 and the start of the second winding, which is H3. Line 2 is attached to H4, and so the end of the second winding, and we jump right over to H2, which is the end of the first winding. So now we have it in parallel. So once again, the rating of each individual winding has not been exceeded. It's for voltage. Let's look at our secondary here now. So on the secondary, because I'm using this as a step-down transformer, and we could use this as a step-up transformer and step the voltage up to 240 or 480, but in this scenario, I'm using it as a step-down. So it's rated at 120 or 240. Okay, so now this is going to be supplying some sort of a load on the secondary. What voltage do I need it to supply? Is this a 240 volt load or is it a 120 volt load? I got a choice, right? So that's what would determine how I would connect up this secondary. So for the secondary, I think of it as batteries. If I take a couple of 12 volt batteries, let's do a little crude drawing here. Okay. If I take two batteries, say they're 12 volt batteries, car batteries right here, that's really crude. And we got poles, there's negative, positive, negative, positive. So if I were to take and connect these up these two batteries in series, say they're 12-volt batteries, and then I put a voltmeter across, I would get 24 volts. If I took these same two batteries and I'm going to connect these up in parallel now, right? So there's negative, positive. So I'm going to jumper the negative over to the negative and the positive, kind of really crude, over to the positive. I would get 12 volts, right? So, but I'd have double the current capacity. So that same concept, if we look at our multi-winding transformer here, that when I apply rated voltage to each individual winding, oh, what's going on here? When I apply rated voltage to each individual winding, so 240 volt, whether it's a 40 volt or 240 volt supply, that just means series or parallel in the primary, I'm going to induce 120 volts here and 120 volts here. So to produce 120 volts, I need to connect these windings up in parallel. So that's a parallel connection. So here's your line 1, here's your line 2. So line 1 is connected up to X3 and X1. Line 2 is connected up to X2 and X4. So now that is going to produce 120 volts because it's in parallel. The two, just like we have the batteries here, the two 12-volt batteries in parallel. What if I want to produce 240 volts on the secondary? Okay. So now I have to put those batteries in series to make 24 volts. Well, same thing here. I put the two 120 volts in series. So now by putting them in series, I get 120 volts induced here, and then I get another 120 volts induced here. So my output is now 240 volt. All right. So I can supply a 240 volt load. Here's something else that we could do with this. Now, each one of these only contributes 120 volts. So if I make a center tap here and I ground this point, what does that look like to you? What would I have for a voltage from here to here? That'd be 120 volts. And here to here, 120 volts. But I add them together, I get 240. So we've just made an Edison 3-wire. So that's essentially how it is. It's a 240 volt induced secondary voltage with a center tap. And so because the terminal points come out in the middle here, we can make that Edison 3-wire. We have the availability of all three voltages. All right, let's keep working with this. So here's the 1000 VA transformer. So let's just quickly review what kind of transformer we got here. We got a 40 volt supply coming in here. So each individual winding is rated at 240. So I have to put them in series so I don't exceed the voltage of each individual winding. So 240 and 240 we'll have there. So if I have, because they're in series, each winding only sees 240, induces 120 here, 120 here. And on the secondary, put them in parallel, okay, to produce 120. So I could have any combination of this. I could have a parallel or a series primary or a parallel or a series secondary. Let's look at the current rating. So this transformer, when we utilize all the windings, it is a 1000 VA transformer. So we can apply this on the primary. If we wanted to go 1000 VA divided by 480, that's going to give us 2.083 amps. So that means maximum current without overheating this is 2.083 amps. Because it's connected in secondary, there's only in series on the primary, sorry, there's only one path for the current. So that 2.08 amps will flow through this winding, then through the second winding. Because we're in series, it's the same 2.083 amps. It is in series. Let's go look at what if we did this and we had a 240 volt supply here on the primary, because that's the way we need to connect it. So let's say that's 240 now. So now I have to connect this in parallel. And so what do we got now? 1000 VA divided by 240. It comes to, what is that? 4.167 amps. Okay? So 4.1, so the current goes up when I connect it up for the lower primary voltage of 240. But has the current exceeded the rating through each winding? Okay? If we follow the path, we got 4.167 amps flowing in, 4.167 amps flowing out. But what happens here is this current splits. Half that, which is 2.083, goes through the 240 winding, first 240 winding, and the other half flows to the second winding. So that's 2.083 amps. So the current splits because they're in parallel. And then when we look at this transformer, well, what's the current going through each winding? 2.083. That's its maximum through each individual winding. Have we exceeded anything? No, we haven't. So we still have a 1000 VA transformer. This same concept applies to the secondary. It's drawn right now with the parallel connection. Okay, so let's start over there. 1000 VA transformer is its rating divided by 120 volts. That is going to give you 8.333 amps. All right. So 8.33 amps for the parallel connection. So current would come out. Maximum current we could pull is 8.33 amps, and it goes back in 8.33 amps. All right, but let's look at what happens here again. It's a parallel connection. So that 8.33 amps would split. Some would go through I'm going to go this way here. So some would come, yeah, that's fine. Some would go through this winding, and some would go back through the second winding because it's in parallel. So it's split evenly. So each one would only see 4.167 amps. And that would be its maximum rating. If this transformer was connected in series, would any of the ratings be, would we exceed any ratings? Well, let's have a look. Okay, so now we're connected up in series. So never mind the parallel connection here. And now we're going to produce 240 here because the voltages will add. So our new secondary output voltage is 240. So 1000 volt amps, divided by 240 volts is 4.167 amps. So then when I draw a load off of this, the maximum load that I can put off of this is going to be 4.167 amps at 240 volt. Because they're in series, it's only one path, and we will not exceed the rating of any individual winding. So each individual winding, if we look here, is rated at 120 volt, 4.167 amps max. Depending on how we connect those, we can either have 240 volt with a maximum of 8.33 amps because of the parallel connection, or that would be 120 volt. 120 volt with a maximum of 8.33 amps in the parallel connection, produce 120 volts, or 240 volt with them in series, and now our maximum current is down to 4.167 amp that we can draw off this. So that VA stays the same no matter what we're looking at, what type of connection. Let's go to our next slide here. Okay. So here's having a better look at that again. Now we've done parallel on the H's, and one H winding is rated at 2.03. Because we put them in parallel, the current is now doubled, 4.167 amps maximum current it can draw because we're in parallel. And so that would be for the 240. The series connection on the secondary here, so now we're producing that 240. The maximum current is going to be that 4.167. All right, 4.167 because we're in series. So that's 1000 VA divided by 240 volts. And just showing you a few different options here. So we got 480 volts on the primary, so we have to put it in series. 1000 divided by 480 is 2.083. We're doing the parallel on the secondary. 1000 divided by 120 volt parallel connection is going to give us a maximum current of 8.33. Because it's in parallel, that current splits, and it's still not exceeding the rating of any individual 120 volt winding. Okay, so we can connect this transformer up for 240 to 240 volt operation, create an isolation transformer. So for 240 to 240, we would put the primary in parallel. So each winding gets 240. We always want to get the maximum voltage on each winding. And it'll induce 120 on the secondary here. 120 will go onto the secondary. Now if I want to produce 240 total, I have to put the two secondary windings in series. Multi-winding connector for 480 to 120. Here's what that would look like. So 480, well, each winding is only rated at 240, so I have to put it in series. Remember, I want to always use all the windings so I get the maximum VA and apply rated voltage to each one. On the secondary, I want to produce 120. So each individual winding produces 120, so I have to put those in parallel. And you can see we have parallel connection here. All right, so an example here. If you like, you can pause this video. I want you guys to guess the connection. On the primary side is the H windings. We have 240 volt coming in. That's our supply voltage. And we want to produce 120 on the secondary. So we have a 2-to-1 transformer. How do you connect this? Well, each winding here is rated at 240 volts. So we want the maximum voltage on each one. Therefore, we would have to do the parallel connection on the primary. Now, by doing the parallel connection, each winding sees its rated 240 voltage. It's going to induce 120 on the secondary on each winding. Now we want to produce 120. What would be the connection on the secondary? That's right, parallel. Okay, so by putting them in parallel, we will produce 120 volts between X1 and X4, and we could connect up our load there. Let's try another one here. So we always want to use all of our windings to ensure that we get maximum VA out of the transformer. That is correct. And we want to make sure each winding gets its rated voltage. So in this case, I have a 40 volt supply and I need to produce 240. What would the connection be? Correct. It would be series on the primary so that the 480 volts would split amongst both windings. So each winding would only see 240. And on the secondary, what connection would we need? Need to produce 240. Correct. You have to put them in series. So now the two voltages would add, because they're in series, to produce 240. Let's try another one. This time you have a 480 volt supply coming in and you want to produce only 120. What's the primary connection on the H windings? Series. Correct. 480 volts, we need that to split equally amongst the two windings so we don't exceed their rating. And on the secondary, we're going to use a parallel connection because each winding will produce 120 across, 2 to 1. 240 divided by 2 is 120. And we want to produce 120 out to supply our load, so we need the parallel connection. All right, on this one, we're going to create a one-to-one transformer, essentially. So 240 in, 240 out. What is the connection on the H windings, or the primary? Well, we want each winding to get its full rated voltage. So in order to do that, we have to put them in parallel. Now each winding will get rated voltage on it. On the secondary, it's going to induce 120 volt on each winding. So we want to produce 240, so we will have to put them in series. So now those voltages on the secondary add, and they produce 240 volts.